Hello, everyone. Welcome to another session on structured streaming. And if you're looking to learn about how to architect structured streaming right, you are in the right place. We have TD. He's an Apache Spark committer and a member of the PMC. He's the lead developer behind Spark Streaming and currently develops structured streaming. Previously, he was a grad student at UC Berkeley and at AmpLab, where he conducted research about data-centric frameworks and networks with Scott Skinker and Jan Stoika. Please welcome TD.
Thank you very much. So people are still coming in, but nonetheless, we can start, I guess. So before I start, let me take a quick poll in the room on how many people are not familiar with structured streaming. Please raise your hand. Quite a few. I'm glad that I put a 5-minute introduction on what structured streaming is. So, okay, let's start. So, structured streaming at a very high level is a distributed stream processing framework built on top of the Spark SQL engine. So the same engine that provides you with all the fast queries, etc., also speeds up stream processing. And it's fault tolerant exactly once, everything that you expect out of a modern stream processing system. And it's got a great set of connectors to work with all the ecosystem of different storage systems around there. And the fundamental philosophy of structured streaming is that you as a developer should not have to think about stream processing. You should only think about your query in terms of a batch-like query. Like, okay, here is my SQL query. It's on a table. And you write that code as if you're writing it on some batch data. And it's Spark's job to automatically figure out how to run that incrementally as more and more data comes in from the input streams. Now, structured streaming has been around for almost 3 years now, and we on Databricks have thousands of streaming applications with hundreds of customers running them on our platform. Collectively, we have trillions of rows. Well, actually, there's thousands of trillions of rows already processed. So it's a pretty big, huge adoption that we have even within Databricks. Let go of the community is much larger. But to give an idea of what structured streaming query looks like, here is a brief example to show you what the anatomy of a structured streaming query looks like. So let's say this is a pretty common case. Let's say you're reading data from Kafka. Your data is encoded in JSON. And what you want to do is store the data finally in a structured table like Parquet. And you want to get end-to-end exactly once guarantee that every record from Kafka gets written out exactly once in the Parquet table. To do this is what you will write. Basically, you will start by creating a data frame on top of the Kafka data. To do that, you have to do spark.readstream, where you specify how to connect to Kafka as an option, what topic to read, etc., an option, and finally call load. This creates a data frame, which is essentially a programmatic API that represents a table, which has essentially columns and a bunch of rows for those columns. So for every record in Kafka becomes like a row in that conceptual table in the data frame. Now, when you're calling load on this, you're just defining that you want the data in Kafka to be conceptually represented as a data frame. It doesn't actually start reading, so everything is lazy. What it returns is this data frame. Now, on this data frame, now you can do your standard data frame operations in Spark, or either using data frame operations itself, or you can directly use SQL on top of it. But what you can do on this is use a lot of built-in SQL functions to actually process the data. For example, in this case, I have the binary payload from Kafka. I want to cast it as a string, treat it as a JSON, parse out the JSON using this inbuilt function called from.json, and then finally, I want to kind of unnest any of the data columns in that and finally save it to Parquet. So I've done these operations. Next step, I say, write out this stream of parsed data into Parquet with the given path. And then finally, I specify that now that the computation has been specified, how do I want to run this computation? In this case, I'm saying that trigger this every 1 minute, so that basically this boils down to a micro batch of every 1 minute of data. Every 1 minute of data gets processed, and then the next 1 minute picks up. You have to You have to specify the checkpoint location, which is where the query will save all the necessary information to restart if there is any failure. Things like which Kafka offsets have been processed, all of that information gets saved to the checkpoint location. And then finally, when everything has been specified, you can say start. Now, when you say start, what structured streaming does underneath is that it takes this code and converts it into a logical plan, which is a pure logical representation of what is it that I want to do. Basically, I want to take some data, read from Kafka, parse it in a particular way, and then write it out to Parquet. Pure logical description. Then Spark SQL's fantastic catalyst optimizer kicks in, and it takes a logical plan, optimizes it in such a way that, that it figures out the plan by which it can best execute the query. For example, all the database logical plan optimization stuff like pushing, filter, push down, et cetera, is done by Catalyst Optimizer, and it generates a very optimized logical plan. And from that, now, this is where the structure streaming part of the Spark engine comes in, is that it takes this optimized logical plan and starts producing a sequence of physical plans to execute data as new data comes in. So this is where the incrementalization happens. And so Spark SQL structure streaming engine automatically takes this batch-like query and starts generating these incremental plans that know how to compute new data from Kafka and how to keep track of offsets, how to keep track of intermediate results between batches, like if you're counting, aggregating, you have to remember the partial count, how to make all of that fault tolerant. The engine takes care of that. And this whole thing is distributed. Therefore, you can scale it horizontally as much as possible. Okay. Yes. Very good question. I'm just going to answer this one question, but please let's hold off all the questions towards the end because I'm worried that we're not going to have some time. But to answer this one question, how is this different from KSQL? Well, KSQL is limited by what you can do in just pure SQL. There are a lot of operations that KSQL cannot do that structured streaming can do. For example, if you have to write arbitrary stateful processing code, KSQL doesn't have support for that. Only structured streaming's DataFrame operations have support for writing a lot more things than what you cannot express in pure SQL. So like for example, if you want to specify arbitrary lambdas, arbitrary UDFs, et cetera, all of those can be specified much more easily with structured streaming than most other systems. Okay, moving on. Okay, so with this query, as this query is running, your data from Kafka is being written out to Parquet, and it is immediately queryable by interactive queries directly from Spark or any other system that reads Parquet. So this is great. This is what a typical structured streaming ETL query looks like. Now, in the past, I've given further deep dives into how each of these operations work, how can explore other types of operations, et cetera. And so those are the talks I've given where I'm deep into APIs and stuff, like given a particular thing that you want to achieve, how do you express that in terms of APIs, et cetera. In this talk, however, I'm going to zoom out a little bit. I'm going to stand back and see that, okay, let's start with the problem. What is the data, and what is that you want to get out of it? And how do you architect the things in the correct way such that you get what you want? And so now you may be asking, this is a streaming design pattern talk. There has been other streaming design pattern talks. I'm not the first one to give such a talk. Why should I listen to your talk? Here's the interesting bit. Most other streaming design pattern talks are based on engines that are purely streaming engine. So often, given a particular problem that you want to achieve, there's only one way of doing it, because it's just a streaming engine. Spark, on the other hand, is not just a streaming engine. It has a lot more than streaming. So given a business problem, there are often many different ways of solving that problem based on what exactly do you want. And it's important to understand those patterns of how different ways you can solve it, because you can accordingly tune your cost, performance, and quality of the output data. And this is why you should pay attention to this talk because I'm going to explore some of the design patterns and how there are different ways of solving that. Now, so this is what the talk is going to be, that how do you think about design in the first place? Like I've seen a lot of people, I've worked with hundreds of customers in the community, not customers. I have seen many, many workloads. Over the last 8 years, I've been working with stream processing. So I've seen a lot of people, flaws in how people think about things. So I'm going to talk about what is the right way to think about designing the streaming pipelines, common design patterns that comes out of it. So I'm going to explore some of them. And with a brief look in the future, I'm going to end with that how are we going to make this easier for you to write and think about in the future. Okay, so let's start from the very basic. When a developer is asked to build some pipeline, this is what they have in front of them. Here's a bunch of data streams. This is what I want out of it, some insights. And that's where the design process starts, that how do I get this from that? So what I'm going to say is that to think about this in the right way, there are 3 questions you need to ask. What, why, and how? First of all, what? What is your input? What is the content of your data? Is it logs? Is it key value data where new values for every for keys are coming in? You have to understand that, what format your data is in, what system your data is in, what are the capabilities of the system, that's the what. What is your output? What is it that you want as insights, as the final result? And what is the throughput and latency that you need? Now, this is the easy part that most people get right, but the hard part is people don't go to the next step and ask, why do you want that output? Like people, who is going to use that output, and accordingly, you have to reason about why do you want that output with that throughput or that latency? And how are they going to consume the result? For example, here are some of the flaws that I've seen over time. People tell me that I want my dashboard with streaming counts continuously updated every second. Like, my first question is, why? Is there any point in updating a dashboard if a human is going to see that dashboard and act on it? Like, is a human going to act on it every second? Or if something happens, is a human going to immediately get to know of it every second? Then if humans are probably going to take a minute or hours to really see that dashboard and act on it, then why do you need to update every second? These are some other mistakes. Second mistake that I've seen. I want to generate automatic alerts with up to the last second count. Well, because something went wrong, etc. But the fine print is that my data is often very late. I have unpredictable delays in the data. So then my question is there any point to really take critical alerting actions on data where the quality of your data is low, that you haven't even received enough data to take good decisions because they are arbitrarily delayed? So then why do you need second scale or lower than second scale latencies? Third one, and there are a lot more, but I'm not going to waste time going through all of these, but here's another common pattern, that I want to train machine learning models on the final results, but somehow, somewhere, someone decided that the final results are going to be in a key value store. Well, that's fine if you're serving, but most machine learning model training those workloads typically scan the entire data iteratively. And key value stores are not great at handling scans. They're great for single key value lookup, not for scans. So somewhere you're not designing the system right. You haven't picked the correct storage system. So it's very important to really ask, why are you doing this? Why do you want what you want? And finally, once you understand that, the next step is how to achieve that, like how to process the data and how to store the results in the correct way. So, and my proposition is that if you understand the what and why, your how will automatically fall out of it if you really think about common design patterns. And that's what I'm going to talk about. Now, I'm going to talk about only 5 of them. There are quite a number of more, but in the interest of time, I can only focus on few. And there may be other patterns that you care about. Please come and talk to me after the talk or in the AMA session later. But I'm going to focus on just a few of them here. The other thing is that since we made Delta Lake open source, I'm going to talk about Delta, how Delta makes a lot of these design patterns easier as well. So you might learn that how structured streaming and Delta is a wonderful combination together. Okay, pattern one, plain ETL. I actually just walked an example from Kafka to Parquet with you in using structured streaming query. I walked through that example, but let's step back and see the general problem. Like, you have as input an unstructured input, JSON or just plain text, can be from Kafka files, etc. And what you want is structured tabular output. And why you want it is because either I want to interactively query that tabular data from SQL, whatever, or there are periodic, daily, hourly jobs that is going to use that tabular data to compute monthly reports, etc. Okay. So now that we understand what and why, let's start digging a bit deeper. Let's say you care about latency of few minutes. The way to solve it is pretty much the same pattern that I walked through, that you use structured streaming that runs continuously, runs 24/7 on a cluster, and it saves the final results into structured scalable storage that support such that all the downstream interactive queries or periodic jobs becomes fast. And typically, it's structured tabular file formats like Parquet, et cetera, are very good at that because they provide all data skipping capabilities, et cetera. Now, in this case, Parquet was great, but Delta Lake is better because Delta Lake allows you to do a lot more. For example, while the streaming query is writing files, et cetera, you can start reading the query with clear snapshot guarantees, even while the writes are in progress. So you don't see partial files, et cetera, et cetera. And concurrently, for many things, as you must have seen Michael's demo yesterday morning, you may have to reprocess the data, coalesce files, coalesce multiple smaller files into larger files, or fix data concurrently, et cetera. All of that becomes possible with Delta Lake's ACID transactional guarantees. So you don't need to worry about how are these things going to handle. And then, of course, querying from a Delta Lake gets you all the beneficial capabilities of data skipping, et cetera, et cetera. Now, let's change the what a bit. Suppose I don't really care about latency that much. It can be hours, but I am a lot more cost conscious. I don't want to have a cluster up 24/7. In that case, there's a different way to achieve this and a much cheaper solution. Instead of running a cluster 24/7, you take the same structured streaming query and just say that instead of triggering every 10 seconds or every minute, I'm going to trigger it once. What that does is that it will run a single batch, process all the data that has been received since the previous batch was run, and shut down the streaming query. And with that, what you can do is that using an external schedule, let's say Airflow or some other external scheduler, like in case of Databricks jobs, you can say that, restart this streaming query on a new cluster every 6 hours. So every 6 hours, the streaming query will start, process all the data that has been received in last 6 hours, and shut down. So you're not having the cluster up and running 24/7 and much cheaper, and you're fine because you don't care about second-minute level latencies. You're fine with hours. Again, but you didn't have to change any code or any of the business logic. Just one line before the start command. That's it. And this is a third option. Sometimes, if your end goal is essentially querying the data interactively, and you want latencies even lower than minutes, like because I want to query the latest last second data in Kafka, you can directly query Kafka using Spark SQL. You can run batch queries on Kafka, treat it like a file system, and you will query the last record that was received by Kafka at the time where the query started. That is also possible, and that gives you even faster results by skipping the ETL step completely. Again, all of these three options are not mutually exclusive. You can do one as well as still directly query Kafka, and as long as Kafka can handle the load of both the ETL query and the interactive query, you're perfectly fine. You can do all of these. Second pattern, key value output. When your input is essentially keys and bunch of new values or some keyed input, and what you want as the output is also essentially keyed out with some key value. Now that value can be aggregations, sums, counts, or it can be arbitrary stateful operations like sessionization, etc. All of that can be built in structured streaming, but ultimately the output is key value. In that case, you have to ask, why do I want that output? There are essentially two common patterns. Either you want that key value output for looking up, that, for example, a dashboard or some website is willing to look up the latest value of a key. Or you want the final summary table with aggregates for essentially interactive queries or periodic jobs, essentially large-scale scan-based analytics. Now, based on that, your decisions are very different. For example, if you just care about lookup, then what you can do is use structured streaming to process. Let structured streaming handle all the stateful operations or aggregations, etc. And then finally write the output into key value stores. And key value stores are great for looking up. They're optimized for that. Well and good. However, and you get latencies like seconds, minutes, whatever range you want. However, if you care about just summary statistics that for interactive querying, large SQL jobs, etc., and you don't care about seconds that much, you're fine with minute latencies, you can write out these aggregates directly into Delta. Because Delta supports, well, as of now, not the open source Delta, but managed Delta Lake on Databricks, it supports upserts using the SQL merge command. So what this merge command allows you to do is say that in the streaming query, there's this operation called for each batch, where you can specify that for every batch's output, what do you do with it? And in this case, you can directly call the SQL command on a Delta Lake saying that merge the output of this batch, which is basically updated values for keys present in that batch, and upsert those values directly into Delta. And this operation, right now only on managed Delta Lake, but we will soon make it available in open source Delta Lake. So stay tuned. And so this is great. Then that means that you can directly update a file-based table using aggregates. So you're getting very close to fine-grained updates. But the whole thing is optimized for doing arbitrary scan-based analytics on top of the Delta Lake table. The other thing is that you need to worry about is that here we are relying on structured streaming to do the stateful operations. But for that to be scalable and what you need to do is set watermarks inside the stateful streaming queries. Again, if you're not familiar with watermarks, I advise you to go and take a look at my previous talks. But what watermark does is it essentially caps the amount of state that state as well as the amount of late data that you are willing to handle. So it buffers the data in memory such that it waits for late data, but only a particular threshold, etc. Now, so inadvertently to limit the amount of memory usage, you have to set watermarks such that you have to say that if the data is late beyond a certain threshold, you drop the data, which inadvertently leads to some amount of inaccuracies if you care about really correct results like dropping no data, and maybe you don't care about latencies that much, which you cannot. You cannot care about late data as well as very low latency together, because to take decisions, you have to wait for the late data to be arrived. Then the other way of doing this is that do not do a streaming aggregation, ETL everything into something like Delta Lake, and then run aggregations on top of that Delta Lake as a post-processing step. And then you know that your final results will be correct if you run the aggregation as a final step in the right way, such that all your late data has been received and stuff. So the latency would be higher, hours, days, depending on how late your data can be, but the results will be correct. So that is also possible in this pattern. The third pattern I'm going to talk about is joining multiple inputs. So, and this is quite common where you have, let's say, two streams of data which has a common key. For example, one stream has sales information of each item that was sold, and the other stream has product information for that item, what was the item's ID, et cetera, et cetera. And you want to create a final table where the sale information is annotated with additional product information. So this sort of use case is common. So now there are essentially two ways of thinking about this join problem. One is either you're joining fast stream with a slow stream. Basically, when I say fast and slow, I mean a fast, high volume, fast changing stream, and a slow stream with relatively much lower volume with much slower rate of change. Typically, this is in the sales product case, typically the changing the product information changes much less frequently than new sales are coming in. So this is, the product essentially becomes like a dimension table, with the sales is like a fact table. And you want to essentially enrich the fact table with that product dimension table. So now in that case, what the nice thing to do is you first ETL on the slow data stream to create the dimension table. And then use the dimension table to join with the fast streaming query. So essentially, this becomes like a stream batch join. So you're joining the fast streaming query with snapshots of the dimension table, which is like a batch data set. And together, finally, you'll get a combined table from enriched with both the information. But there are two caveats that you need to worry about. If you're saving the dimension table in standard, Parquet, et cetera, then what happens is that when a structure streaming query starts, it only takes the snapshot at the time of the query has started and uses that for the rest of the duration the query is up. So if the dimension table changes while the other query is running, the new data is not loaded back. And that is fundamentally because the structure streaming query does not know when there is new data, so it cannot keep checking arbitrarily. It just knows way to figure out from the metadata whether the dimension table has changed or not. So that means that changes to the dimension table will not be visible and used by the join until you restart the query. This is often fine if your dimension table changes slowly enough, like once a day. You can plan for it and restart the structured streaming query once a day after the dimension table has been updated and stuff, but not great for other use cases where it is not that slow. So a great suggestion is using Delta Lake instead to save the dimension table. And because of the structure that is present in the Delta Lake with the transaction log, et cetera, we know precisely when the Delta Lake table has changed. So structure streaming can automatically figure that out and automatically reload the new version of the Delta Lake table without stopping the structure streaming query, which is great. But the second caveat is that the other corner case that you need to worry about is that still delays can be complicated reason about. For example, let's say you get the information of a sale of a product, of a new product, which has not yet been populated in the product dimension table. That means that the join doesn't work. You may do a left outer join and stuff, things like that, but your product hasn't been joined. You will have nulls, and then later you need to fix it. So what this doesn't account for is delays in one side of between the two queries. So to solve that, you can treat this as a joining fast and fast data. So essentially there are two fast streams of data which can be delayed between themselves arbitrarily. And then what you want is to take into account that there may be delays, buffer that you want to appropriately buffer the data so that ultimately the join result is still correct. And then structure streaming natively supports stream-stream joins. So data will be essentially from both the streams will be buffered as state as long as you specify that I want to handle this much late data using watermarks again. You can specify that. And how much delayed the data can be within the two streams, et cetera. You can read more details about that in the programming guide as well as in my previous talk. But this will take care of handling delays on both the streams and providing correct results. The fourth pattern I'm going to talk about is change data capture. And this is a very common pattern we have seen. I have seen in enterprises where they have a transactional table where all the OLTP-style transactions go in, all the sales data, et cetera. And what they want to do is essentially mirror that table into a into analytical tables so that they can run scan-based analytics, because they don't want to obviously run large queries on the production transactional table in MySQL or something. So essentially they get a change log from MySQL or some other database and want to essentially generate the final table, copy the final table using that change log. And again, merge that we support in Delta Lake is great at this, because it can take all these inserts, updates, sequence of changes, deletes, and just apply them onto a data lake using merge, which incidentally also supports both not just updates and inserts, but the extended merge syntax of deletes as well, conditional inserts, conditional deletes, etc. Not many databases in the world actually supports these extended merge syntax, but we do, which makes a lot of things very easy. And finally, the fifth pattern I'm going to talk about is how to write to multiple locations. As you can see that in this previous things, from the data, you may want different things out of it. For example, you may want to save both the raw logs as well as the summary tables. You may want to save both the change log as well as the updated table. Or you want to have summary analytics for both looking up as well as for downstream scan-based analytics. So in that case, you essentially want to write to two locations, maybe the same data, maybe some derived data, etc. Now, typically, there are two ways to deal with multiple outputs. One is serial or parallel. But each of them, just thinking about serial and parallel has each of its own problem. For example, with serial, what you're effectively doing is that the first table that you're writing out has to be read again. So the same data, it needs to be read and written once again, which essentially may not be very cheap. Well, it depends on the nature of the table, whether it's cheap or expensive. It could be that the size of the table is small, so reading it once again is cheap, so in which case it is fine. But you have to really wonder what is the size or the format of the table such that you can argue whether it's cheap or expensive. In the parallel case, we have a different problem. You're reading the source data multiple times. So if, for example, you're doing a very expensive operation in the beginning, like parsing the data from JSON or some arbitrary unstructured format to structured format, you will be duplicating that work twice in the two parallel pipelines, which is, again, not great. You have to reason whether that is cheap or expensive. You have to also reason about whether the source itself can handle the load for reading it twice. For example, some systems like Amazon Kinesis has limits on the read data rates and stuff. So you have to be aware of that. So typically, what you'll end up is a combination of both of these, serial parallel, where one idea is that you do the expensive operation first once, and then you convert it to a table that is much smaller and cheaper to read from again, and then you do multiple further downstream operations, which individually they are much cheaper. That's one. But still, you are, again, reading and writing table one multiple times, so it's not the best. In some cases, you can avoid that by using for each batch once again, where a single streaming query computes everything and then writes it out to both locations. This is great for things like you want to compute streaming aggregates, a summary or something, and then write it out to both a delta table for scan-based analytics as well as to a lookup table, key value store for lookup. And so using for each batch, you can take the output of each batch and write it out to both locations. But something you need to be aware is that while this is potentially cheaper, you lose exactly one's guarantee because of the lower level semantics of how for each batch works. So something to be aware of, but there are options of doing this. So now once you have done all of this, you have combined a lot of things. Slowly your pipeline starts looking a lot more complex. For example, our production pipeline looks something like this. We have data from various different sources. We have bronze tables that just dump the data in a structured format, silver tables that cleans it up further, and gold tables which are summaries, et cetera, that are perfect now for reporting and streaming analytics, et cetera. Now, it's actually productionizing just one of this pipeline requires a lot of unit testing, integration testing, deploying, monitoring, upgrading, et cetera, et cetera. And you should actually look at Burak's talk, which he gave yesterday, about productionizing structured streaming jobs. It's a great talk, going through the entire process. But we realized that that is not enough because what you don't care about just one pipeline here. You care about the end result, the streaming analysis reporting, and you care about the entire DAG of pipelines here that given the input, is my final output correct or not? So we need to productionize the whole thing. And that's why we are working on building new, a layer above all structure streaming and Delta, a set of declarative APIs that with which you can specify the entire DAG and manage the entire DAG. For example, to a brief glimpse, again, none of the details is set in stone here. We are still working on this. But the idea is that it's a small library on top of Apache Spark and Delta, and with which you can just specify that what are the nodes in this graph, essentially the sources and sinks in this thing, and what is the specification of the flow between these sources and sinks. And with this declarative definition of the entire DAG, we can automate the process of specifying like expectations. The expectation stuff that you saw in Michael's demo yesterday morning can plug in this thing that along the pipeline you can set different expectations and which can be automatically tested, unit tested with sample data, integration tested with production data. All of that can be done and managed through this simple library. And deploying, upgrading, rolling back both code and the data that needs to be rolled back because the output was incorrect, because it failed expectations, etc. All of that can be done using this library. That's our hope. We're building this, and hopefully we'll be able to announce something in the next Spark Summit Europe, so stay tuned. And that's about it. Thanks for listening. There's 4 minutes, the clock says, I can answer questions.
Hey guys.
And please come to the AMA at 4 p.m. today if you have any more questions.
Yeah, we have 4 minutes, so if you have any questions, please come to the center.
So in the first pattern that you showed, the trigger once option, now if you do the trigger once and it goes and reads the data, I mean the source still has all the previous data too, right? So how are you handling that?
Sorry, could you repeat?
If you go to pattern 1 where you said trigger once, if you want, right? So you said basically you do an external scheduling of the job, so it will go and read the whole thing again. But are you assuming that the data that was read on the previous day has been cleaned, but what if the data is still there? So then what about the duplication?
Which data? The input data?
Yeah, the input.
The input data can still be there in Kafka, for example.
Okay.
But since you're using structure streaming, it is using the checkpoint location to keep track of what has been processed already.
Oh, so
you're just running structure streaming,
okay,
except instead of running batches continuously, you are explicitly triggering that run a batch now, run a batch now, run a batch now. All the existing checkpointing mechanism of keeping track of what has been processed will just work. You have
okay, I get it. So the second part is, why not just set the time interval within Spark streaming itself, like instead of like 1 hour, like 24 hours?
Well, because if you set the timing, you can set the timing in Spark streaming itself, but for that to work, the Spark cluster is up 24/7. If you don't care about that low latency, you can save a lot of money by shutting down the cluster after processing it every few hours.
Okay.
That's why can be much cheaper. And that's a useful pattern to know to save costs when you don't need to spend that much.
Makes sense. Thank you.
We got time for one more question.
Hi, my name is Siva. I have a question regarding Delta and structured streaming. So when we have cascading Delta and structured streaming pipeline, is it better to use row format kind of tables? Because all the time when you are doing streaming, you are reading whole row, right? And when you store it as a columnar file, it's basically needs to like create the whole row every time. And it will increase the speed, right?
So first of all, you're talking about structure streaming and Delta, right? Yeah. So Delta is saving all the data in Parquet file format. That itself is a columnar row format.
Yes.
So to get more efficiency out of that, you can tweak the row group sizes and stuff, etc., of Parquet. But typically, for most use cases, we have seen that doesn't give a lot of benefit in general. It takes a lot of effort to really tune. So you should rather just see what is saying, and only if the requirements are strong enough that it's worth it putting in that effort, do you start tuning or even considering other formats and stuff.
And a query directly on Kafka, will it work for old data? I mean, like 2 hours data or something like that? I
Sorry,
mean,
could you repeat
you
that?
told about querying on the Kafka itself using Spark
Yes.
SQL, right?
Yes.
Will it work for old data, like 2
As long
hours?
as the data is in Kafka, you
Okay.
can query it. So you, while querying, I didn't go into the API level details because
Okay,
I didn't
so
have
we
time.
can have
You
that
can
little-
say that
okay.
what range to query. Do you query from earliest to latest or specific specific offset range to query? You can specify all of that.
Okay, so if you have more retention period, you can query all that
Yep.
stuff. And spark.read.json, it's a general question. Like spark.read.json basically scans whole RDD of string to figure out the JSON schema. Means it's not working as an action. I mean, it's still as a transformation. Means it does action work, but it's not able to persist kind of. Do you have any idea why it's designed like that?
That's a very specific question. Let's talk
Yeah.
offline because the devil is in the details.
Yeah, thank you, Ren. I believe TD, you will be available in the back for
Yep.
more questions, and he also
I
has
can
an
be
AMA at
outside
4.
if you have any more questions.
Yeah.
Let's leave this room for the next speaker.
Yep. Thank you.
Thank you
everyone.
very much, everyone.